Welcome to the 2018 Chermeda Lectures in Science, and we just in the last hour found a picture of John Chermeda. This is courtesy of the university libraries that via the College of Science Communications office. People were scrambling to find a picture. I literally got this in my inbox about an hour ago. So now we can see what John Chermeda looks like. Class of 35, he was actually a chemist, and he endowed this lecture series for the College of Science, and it rotates among all of the departments in the College of Science. And since there are 7 of them, that means we get a statistics-related lecture about every 7 years. Before I tell you a little bit about the history of this lecture series, I want to thank some people, and most of the work has been done by folks whose names you see in front of you. In particular, Ling Zhou has done an enormous amount of legwork in organizing this whole event. So thank you very much, Ling Zhou, for your leadership on putting this together. And the rest of the committee was involved in helping select our distinguished speaker. The 3 names you see at the bottom of the list, Lori, Mel, and Kathy, are members of the excellent staff of the Department of Statistics. And I think everybody knows that that means that they did all the real work. I don't think Mel and Lori are here, but Kathy may be in the room. Kathy, are you here? No, she's probably running around like a crazy person doing something. Sometimes Kathy's filming things. So I will thank them in their absence. Again, the staff just did an enormous amount of work making this all possible. So like I said, we have about every 7 years, this comes back around to the statistics department, and in the past we've had some big names. Well, one of them you might argue is not so much a statistician as a mathematician, but you know, for John Nash, we're willing to make an exception. Right? If you win a Nobel Prize and you have Russell Crowe play you in a movie, then I guess you're allowed to be called a statistician for the purposes of this lecture series. The second in the series of statistics-related lectures was in 2010, and that was by Steve Stigler at the University of Chicago. He's probably the world's foremost historian of statistics, and that's fitting for today's talk because the lecture that you're about to hear has a very strong historical theme to it. And as we sort of look back, I also want to look forward just a little bit. I love this quotation. And you know, statistics, as you will hear, has a very long history, but statistics is also very much in the news. It's very current, it's very topical, and of course everybody knows about data science, big data, data mining, and so forth. And I love this quotation. I think it sounds very current. If you're familiar with this field, you might think that this was written very recently. But in fact, I pulled it out of this pink book here. This is our speaker. He wrote this in 2003, which was actually amazing to me when I saw this right in the foreword of this book. This book has the somewhat funny title, All of Statistics. And in the very first sentence of the foreword of the introduction, Larry says that all of statistics is, of course, an exaggeration. But this is a fantastic book, and it really covers a lot of statistics. And he's targeting specifically this book at people who may not have any background in statistics, but just want to learn a lot about it. So it's a fantastic book. In fact, it won an award in 2005, one of the many awards that Larry has won. So Larry Wasserman, whom you see here, and whom you will see in person in just a few minutes, is the UPMC Professor of Statistics and Data Science. He's in both the departments of, and this is complicated, Statistics and Data Science, that's one department at CMU. He's also a member of the Department of Machine Learning at CMU, and of course both of those departments are world-class. Larry was the 1999 winner of the COPS Award in Statistics. Some people call that the Fields Medal of Statistics, or as we like to call it, the Fields Medal is the COPS Award of Mathematics. It's sometimes called the Nobel, but it's actually limited to somebody who's under 40, and it's given once a year to sort of the top statistician under 40 in the world. And he was the 1999 winner. He also won in 2002 the prize in statistics from the Statistics Society of Canada and the Centre de Recherche Mathématique, and that's given to a Canadian citizen who's basically very, very good, and still less than 15 years from their PhD. I mentioned that this pink book here had won an award. This won the 2005 de Groot Prize, and this is from ISBA, the International Society for Bayesian Analysis. And this is for basically a book. It's not given every year. It's given whenever it's appropriate to an excellent book, quote, concerned with fundamental issues of statistical inference, decision theory, and or statistical applications. And I think that you'll find that a lot of Larry's talk is very much on those themes. Larry is a fellow of the American Statistical Association, a fellow of the Institute for Mathematical Statistics, a fellow of the American Association for the Advancement of Science, and as of 2016, a member of the National Academy of Sciences. He's also the selected giver or presenter of the 2013 Reitz Lecture. This is from the IMS, the Institute of Mathematical Statistics. And this lecture is to be, quote, of broad interest and to serve to clarify the relationship of statistical methodology and analysis to other fields. And again, I think that you'll find that that's very much along the same lines as the lecture that Larry's going to deliver today. And before I get into that, let me just give you a bit of an advertisement for tomorrow's talk. So Larry's here to give 2 talks, and the second one will be not next door. 104 is actually across the hallway. Yeah, that's right. So 104 is our usual statistics colloquium room. Tomorrow's talk will be at the usual statistics colloquium time, and it will be a slightly more technical talk, but of course everybody is welcome to attend that as well. In just a few minutes, he's going to tell us about the greatest debate in the history of science. And with that, I'd like to ask Larry to come up here. We have a certificate for him. Turn this off and speak really loudly. So let me just read you what the certificate says here. So the John M. Chermeda Lecture in Science presented at the Pennsylvania State University on March 14, 2018 to Larry A. Wasserman. Professor Larry A. Wasserman is selected as the John M. Chermeda Lecturer in Science for his innovative and pioneering work on the development of statistical theory and methods in data science, machine learning, computational biology, and astronomy. He has made foundational contributions to high-dimensional inference, clustering, non-parametric inference, topological data analysis, and astrostatistics. So Larry, it's a wonderful thing to have you here. Thank you very much.
Thank you so much. Let me put this, this is on. Can you hear me? I don't even know if this is doing anything. No. Well, first of all, thank you for the wonderful introduction. And thank you for inviting me. It's an honor to be invited to give a lecture in this series. I did notice that in the previous stats lectures, although Steve Stigler wore a tie, John Nash didn't. So, continuing on that every other lecture basis, I'm not wearing a tie today. But it really is a pleasure to be here, and thank you for your hospitality and for all the people who helped organize the event. I know a lot of work goes into these things, and I really appreciate it. So, I puzzled for a while, what should I talk about? Because I know it's supposed to be accessible to a very broad audience, and obviously a lot of non-statisticians. So I wanted to talk about something that would be hopefully interesting, but also convince you that statistics really has some interesting thoughts and philosophy behind it. And what I'm about to talk about is something that I had given up talking about many years ago. I thought, this is all settled, we don't need to argue about this stuff. It's the kind of thing that people used to argue about in statistics when I was a graduate student and when I was young. And then we all sort of made peace and got over it. But now it's become relevant again because statistics is everywhere all of a sudden. And it's my experience that these same issues that we thought we had dealt with all these years ago actually still arise. And so I think, much to my surprise, I find myself talking about it because I think it's still relevant. And there's a lot of confusion here, confusion caused by statisticians, to be very honest. Let's see if I can figure out how to. So here's the question I want to talk about. I'm just going to quote a couple of studies. So I'm sorry, they're streaming this, and I'm not supposed to wander too far from the camera, but I'm going to have to turn the slides. Oh, maybe this thing. Does this turn the slides?
I'm not sure about that.
All right.
This is your
That's the laser pointer and forward and backward laser pointer. All right, I think I can handle that. All right, so, whoops, no, apparently I can't. I'm pushing the wrong button. All right, I don't see it here. Anyway, okay, I'll just go like this. So, here's a Canadian study, recent Canadian study about the flu vaccine this year. So we are 95% confident that the effectiveness of the flu is between 0.25 and 0.55. Okay, that's fine. Here's another study I found. All this is on the internet somewhere. The IPCC, what does that stand for? Intergovernmental Panel on Climate Change, also says they're 95% confident that humans are the main cause of global warming. And the question is, and this is especially relevant in this era of data science that we live in, is what do these numbers mean? What does the 95% mean in the first case and 95% mean in the second case? And I'll tell you the answer at the end, but they mean two different things. The same word, confident, is being used in two different ways, and we've done a bad job, I think, of explaining this. So the debate I'm going to talk about is something called Bayesians and frequentists. Another example of statisticians not knowing how to come up with good names for things. One of the reasons why computer scientists get funded more than statisticians. But it's, what are these Bayesians? So I'm going to assume that most people here don't know what this means. I'm going to explain what they mean and show you that they really are different by giving you an adventure in flatland. That's going to be the highlight, is the high-tech graphics I'm going to use when I show you flatland. So what do these words mean? That's what I'm going to talk about. And why does it matter? And it actually does matter. And it's a little bit of an exaggeration. It's a matter of life and death, I said. So why did I call this talk the greatest debate in the history of science? So there's a lot of debates. Well, first of all, it was I thought, a flashy title, and might get people to come. But also, you know, there's a lot of debates in science, obviously, and they're all interesting and fascinating. So like in physics, what is the theory that will combine general relativity and quantum mechanics? There's a lot of debates in various fields. But this one has a little bit of a different character because it actually does matter. When you go to take a medication which is approved by the FDA, it won't matter whether string theory or loop quantum gravity is correct, but it will matter whether they use Bayesian or frequentist methods. So there is a real sense, it's only a certain amount of exaggeration to say that it's a matter of life and death, because all the decisions you make, medical decisions and so on, really do, it does matter which approach or philosophy to statistics one uses. So I thought I'd say a word, though, about what statistics actually is, because presumably a lot of non-statisticians here, and especially today, when there's all these different phrases, statistics, data science, machine learning, and I'll just tell you my own view I'll spend 20 seconds telling you that to me they're all the same thing. They're all about learning from data, and they're just done maybe in different buildings or on different departments or by different people, and so they get different names. Like the joke I always make when I'm teaching, is that if I'm teaching in the machine learning department, I call it machine learning, and if I teach the same thing in Baker Hall and the statistics, I call it statistics. But it's pretty much the same thing. So to me, all of this is the same thing, and we'll be talking about statistics, but you can think of it as data science or machine learning if you like. And I'm going to focus in particular on statistical inference, which is basically the kind of thing you saw on the first slide. We're just saying I'm 95% confident about something. So here's the setup. We're going to observe something, and it's just going to be some data. Now in general, the data could be just about anything. I've written him here as x1 to xn. You can think of them as numbers, like how many people got the flu. You can think of them as vectors. Nowadays, they could be images. They could be videos. They're just objects. And we want to know something. And that's why we collect data, is we want to know something. And what is it we want to know? Well, let's say theta. Let's think of theta as the effectiveness of the flu. You know, if I give a bunch of people the flu shot, some fraction will still get the flu or not get the flu. That will be what theta is. So we have something we observe, data, and something we don't know, theta. And so this is the example I started with, which is that N people are given the flu, and we want to know the fraction that will be protected by the vaccine. So let's talk about these two different approaches to statistical inference, Bayesian inference and frequentist inference. So in the Bayesian world, first of all, you always use probability whenever we're doing statistics. And in the Bayesian world, probability is interpreted as a degree of belief, how sure are you of something. So you might, for example, say the probability that Shakespeare was actually a pseudonym for Edward de Vere is 83%. And that just means I'm 83% convinced that Shakespeare was a pseudonym for this guy Edward de Vere, which apparently is, some people believe this is true. And that's just, somebody else might have a different probability for that. It's just a number between 0 and 1. And the nice thing about Bayesian inference, and the reason why it's so popular in many fields, is because the mechanics of Bayesian inference are pretty simple. We start with what we want to estimate, let's say the flu vaccine, and we start with this thing called prior distribution. It's just some way of encoding everything we know about this number we're trying to estimate. Then we get data, and then there's a rule called Bayes' rule, which says take your prior, do something with the prior and the data, and you get your updated degrees of belief. And this is called a posterior distribution. So we write this like, I might say the probability that the flu vaccine effectiveness is between 0.3 and 0.4, given the data is 95%. And statisticians, instead of writing the word given, we just put a vertical line. And that's the whole game, is you start with your prior beliefs. Try this again. Okay. Then you start with the, oh, maybe let's try this one. Ah, there we go. I figured it out. Okay. Start with the prior beliefs, you get your data, you apply this mechanism, this mathematical rule to get your posterior beliefs. That's the updated beliefs. And this is very, very useful, especially in, if you're a scientist, say in astronomy, for example. I can use astronomy as an example because I happen to work in the area, and it was pioneered here by Jogesh Babu and Eric Feigelson, by the way. They're one of the first astrophysics centers in the world. And I know that they can attest to the same thing, that a lot of our colleagues in astronomy like to use these Bayesian methods because that's the whole thing. If they want to estimate the Hubble constant, they put a prior distribution on it, they get some data, they run this thing called Bayes' rule, which is a very mechanical rule, and the answer comes out. So it's very automatic in that sense, and that is one of the nice things about it. All right. So a picture of it would look like this. That you have something you don't know, you have your prior beliefs, that's just saying this, I believe this is more likely, this value of theta is more likely than this value. Then you add in your data, you use this mechanical rule to get out the posterior, this is your updated beliefs. This is the prior plus the data. So the prior goes to the posterior with Bayes' rule. Very, very beautiful and elegant way to do data analysis. So what is this other thing called frequentist or sometimes classical inference? It looks the same, but it's slightly different. I'm going to compute two numbers, call them left and right, and they're just, think of them as algorithms on the computer. You pump in the data and out pop these two numbers. It doesn't use Bayes' rule, it uses some other calculation. And then I'm going to say my algorithm produces these numbers left and right. That's going to trap the true value theta 95% of the time. So I'm going to put in the data, outcome left and right. They either trap the true value or they don't, and that's going to happen 95% of the time that they will. And that sounds very, very, very similar. So we call this set of numbers, left and right, a confidence interval. That's a picture. So these are just 20 different people doing 20 different experiments, all using, say, my code for computing this confidence interval. And in each case, there's some value they're trying to estimate, maybe flu effectiveness, maybe something else. That's the black dot. But they don't get to see the black dot. They just get data, and they compute this interval using my software, and sometimes that interval they compute traps the true value, those are the red bars, and sometimes it doesn't, that's the blue bars. But I can tell you this, 95% of them will contain the true value. And so that's the whole frequentist approach. So what's the difference? Well, for the Bayesian, the goal is to express and quantify and update our personal beliefs about some quantity we're trying to estimate. For the frequentist, we want to create software that produces this interval, and we want to say how often does it trap the true value. Does that sound confusing or what? When I teach this to students, they always say, what's the difference? That sounds like exactly the same book. It's very hard to see the difference. It's so hard to see the difference that I will even say that many of our PhD students, our senior PhD students, come to talk to me about this because they say, even though they've done all these hard math courses and all of these, they still think, isn't it really the same thing in the end? It's very hard to distinguish these two things. But it is different, and I'm going to convince you of that. But before I do, I want to mention what I call binomials, Bayesians and name only, because this adds to the confusion, unfortunately. So I mentioned that part of the mechanics of using Bayesian inference is to use this particular mathematical rule, which happens to be called Bayes' rule, which is why it's called Bayesian inference. But using Bayes' rule isn't the same thing as doing Bayesian inference. You can do Bayesian inference without ever using Bayes' rule, and you can use Bayes' rule and still be doing frequentist inference. How's that for confusing? And this confusion leads to these binos, I call them. That is, there are people who think they're Bayesians, but they're Bayesian in name only. And in other words, they're using Bayes' rule, but they still have the frequentist goal, which is, what are the frequency properties? How often will I get to track the true value? So their goal is to get good long-run frequency behavior. They want to say, if I gave the software to people and they used it, they would track the true value 95% of the time. Nothing about beliefs, even though they're using Bayes' rule. So here's two examples. Nate Silver has a fantastic book, I'm sure many of you have read it, Signal and Noise. And I do like the book, but he spends a big part of the book trashing frequentist methods and saying how wonderful Bayesian methods are. And then if you read the rest of the book, he spends the rest of the book doing frequentist inference. He's got all these charts showing that his 95% predictions are right 95% of the time. He's looking at long-run frequencies. So he's confused using Bayes' rule with Bayesian inference. And he's a pretty smart guy. Another one is, and this is another great book, by the way, The Theory That Would Not Die, How Bayes' Rule Cracked the Enigma Code, Hunted Down Russian Submarines, and Emerged Triumphant from 2 centuries of controversy, by Chermeda Lecture. Great book, but the whole book is confusing Bayes' theorem with Bayesian inference. She's talking repeatedly through the book about the use of Bayes' theorem, not about this Bayesian approach to statistical inference. So this is quite common. So what is the difference? Are they really actually different? Well, here's the problem. Here's 150 years of confusion that has been caused by, in my opinion, bad notation that we statisticians invented. Which is that there's beliefs, how strongly you believe something, and there's frequencies, how often something happens. And they're just two unrelated quantities. And unfortunately, every statistics textbook, including my purple book there, makes the same mistake. We use the same symbol, P of A, to represent the probability, even though sometimes it's referring to beliefs and sometimes it's referring to frequencies. And the whole confusion could have been avoided, I think, if we had just put B of A for beliefs, F of A for frequencies, and nobody would expect them to be the same. We use two different things. And unfortunately, we use the same symbol for both. And yes, I'm guilty of that too. So your 95% Bayesian interval, that's something about my beliefs, doesn't have anything to do with tracking the true value 95% of the time. Very subtle point. So to illustrate this point, it's one thing, I always say this in class, I tell students this, but they can't picture how they could be different. So what we need is an example. And so we're going to take an adventure in flatland. This is one of my favorite examples. It's due to the British statistician Mervyn Stone. Many years ago I had a blog, and I put this example on my blog, and I was shocked by how many well-known senior statisticians wrote me and said, you got this wrong, this can't be right. They thought there was a mistake in it or something like that. And it just surprises people. It's kind of like that, what's it called, the Monty Hall paradox, some of you may have heard, where people don't believe the answer until you actually do it. And this is a little bit like that it seems to surprise people. So here's the deal. This is my fancy graphics. For me, this is high tech. So here's the idea. I'm starting here. I'm in the city, which these are buildings, and these are roads in between. And I start out here, and I just randomly walk through the city. But as I walk, there's an elastic band behind me attached to this starting point. And as I walk, I'm stretching out this elastic band. But if I take a step backwards, the elastic band disappears because it's elastic. Okay, so if I took a step up here, it would get longer. If I took a step back here, shorter. And I just keep doing that. I just keep wandering around and around and around for a long time. Finally, I get tired, and I stop. And I drop a treasure. And there's my treasure, that X. That's where the treasure is, and I bury it. Now, I decide to make things difficult for you. I'm going to take one last random step. So I'm either going to go north, west, south, or east, and I'm going to take a random step. And that's what you're going to see. So what you're going to see is me standing here, but you don't know where I put the treasure. Here's all you see. I'm standing here. Here's this elastic band. And you know that the last thing I did was I took a random step from somewhere. Well, there can only be 4 places. I could have been up here and taken a step down. I could have been here and taken a step left. Step here, taking a step right. And here, taking a step up. You don't know which one. All you know from this is one of these 4. Okay, so let's do some statistics. You think about this and you go, okay, here's the 4 possibilities. Treasure was here and that was your last step. Treasure was here and that was your last step. And so on. This is just those 4 possibilities shown as 4 pictures here. I was either to the west, north, east, or south. So the location of the treasure, there's only 4 places. And I'm going to sweep a few details under the rug that the statisticians will have to forgive me for. We're assuming a pretty smooth prior over the set paths. And Bob the Bayesian will conclude that those 4 possibilities are equally likely. The posterior puts probability 1/4 on each of those things. That's where I'm putting in the smoothness on the prior. Let me just go back and say that again. We know that I chose a guy at random, a direction at random to take my last step. And so in technical terms, the likelihood is exactly the same in all 4 directions. And when I do this Bayes' theorem thing, which is combining this prior on my set of paths with the data, which is where I ended up, it turns out each of these 4 cases is equally likely. A posterior distribution puts belief 25% on each of these 4 possibilities. Okay, so in particular, I'm going to be very generous. I'm going to pick three directions. So he says, great, 3 directions. They're all equally likely. I'm going to pick west, what were they? I forget. West, north, and east. He's going to say, since each one of these to me has 25% belief, I'm going to just pick these 3. And that gives me a 75% chance, that's my belief, 75% chance that the treasure is either here, 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 here. And that's a correct calculation. He's done the mechanics of this Bayesian method correctly. So, pretty good. But Franny, the frequentist, picks the opposite. Instead of west, east, or north, she says, I'm just going to pick 1. I only need 1. one guess. And I'm going to pick south, the opposite of your guess. And Bob's shaking his head, well, she's crazy. She's like, I'm going to have, my belief is 3/4. My belief that she's right is 1/4. So Bob has this set of 3 possibilities, west, north, and east, and he's this very strong belief of the treasure, and he's done this mathematically correctly using Bayes' theorem. Franny said nothing about beliefs. She just says that this south thing is what she calls a 75% confidence interval. In fact, she's constructed it by picking the direction, as you can see, that makes the string the shortest. And what's going to happen? So there it is. There's Bob's set is the black 2 sets. There's where I'm standing, and south is what Franny picked. Who's right? They can't both be right, because both of them are now going to claim that they're 75% confident in their answers, just like at the beginning of the talk. They both claim they're 75% confident in their answers. Well, they're both right. And this gets to the issue of not one of these theories being right or wrong, but there being 2 different theories. One about beliefs and one about frequencies. Bob is reporting his beliefs, and he's doing so correctly. He started with some beliefs about where the treasure might end up. He got some data, and he followed the mathematical theorem, and got the posterior distribution, and he's 75% strong belief in that set he chose. Franny is reporting a method that she claims will win the prize at certain frequencies. In fact, here's a good exercise for graduate students. Go program this and play the game over and over again. And you're going to see that Bob wins 25% of the time. The 75% set is a statement about his belief. It's nothing about how often he will actually trap the true value or find the treasure. Whereas Franny will win 75% of the time. And it's one of those things that some people say, okay, and then some people say, this cannot possibly be true. People have different reactions to it. But if you have any doubt about it, just program it and see what happens. And you'll see that Franny is going to win 75% of the time. The point here, again, is just terminology. Bob's beliefs have nothing to do with how often you're right, which is a frequency statement. Bob's beliefs are 0.75. Franny's frequency probability of getting the treasure is 75%. Bob's beliefs, Bob also could have frequencies. How often is he going to win the prize? Actually, only 25%. It just has nothing to do with his frequencies. Okay, so that might seem disturbing or not disturbing, but both answers in some sense are correct, even though they seem to disagree with each other. Both people are claiming 3/4, but they just mean 2 different things. Okay, so that's fine. The problem here is, what does this have to do with actual data analysis? What does this actually have to do with science? What does this have to do with what you learn in the statistics course and so on? Well, here's the thing. In the olden days, so I'm going to say, I'm calling when I was a graduate student now the olden days, maybe it wasn't that long ago, statistics dealt with fairly simple data sets. I used to work in our consulting lab in our department, and I did a lot of statistical analysis. But we didn't have very complicated data sets typically. The number of things we were estimating, the parameters as we call them, were usually not maybe 3 or 4 parameters, maybe a few more. And the truth is that in these simpler models that we dealt with years ago, there isn't a stark difference between the Bayesian beliefs and the frequentist probabilities. The example that I showed you was constructed particularly to show a stark difference. But this is not typical. This is not what typically happens. And so, in those days, it was really just, everybody would analyze data, they'd use their Bayesian or frequentist methods, and they'd get almost the same answer. In fact, a lot of textbooks made a big point of showing that the 2 methods were approximately the same. And yet people love to argue about it. You go to the bar afterwards, and there's these furious arguments about what should you be doing using a Bayesian philosophy or a frequentist philosophy. And it was kind of ironic when you think about it, because it didn't really affect statistical practice very much in most cases. And yet people would literally not talk to each other and get very angry about this. There was even a whole group of people who felt so disenfranchised, people who were favoring Bayesian methods, they felt so disenfranchised, they formed their own set of statistical meetings, which were quite famous meetings, called the Valencia meetings, where the Bayesians felt like they could go and all hang out together and not be subject to harassment, intellectual harassment. And I have to say they had pretty good parties. I hung out a lot with the Bayesians in those days because those conferences were a lot of fun. I give credit for that. But it didn't really matter in some sense. In fact, the truth was in those days you couldn't even compute the Bayesian answers. This was all either done mathematically or there was a lot of philosophy, but nobody actually knew how to compute the posterior in anything but the simplest models. So an example of this is that you can see is I'm trying to predict some y, like your blood pressure, from some features, x1, x2, x3. These might be some certain genes. I have 3 genes I've only measured on you, and I'm trying to predict your blood pressure. And we would put down a model, which is what's a statistical model. It just relates the data, different parts of the data to each other. So in this case, the outcome, the blood pressure, we might say it's some linear combination of these genes plus some error, and you can see that there's these things here, these betas, these are the parameters we don't know. So I'm saying blood pressure maybe is a linear combination of 3 genes, but we don't know the linear combination. But you can see I only have to estimate 4 parameters. And if I have a few hundred data points and 4 parameters, and if you send somebody off to do a Bayesian analysis and somebody off to do a frequentist analysis, it's not going to turn out like the flatland example. Typically, they're going to end up with almost the same answers. And that's because, again, we only have 4 parameters to estimate. So I'm just making this point that I just made. The statisticians argued about it all the time, but when they analyzed data, it was very rare to see cases where they differed very much. There were some, of course, but there weren't very many. Now, when it came to more complicated models, the problem was that Bayesian inference was kind of stymied. There was no way to do this thing called Bayes' rule, which is mathematically very simple, but computationally turned out to be very, very demanding. Then something happened, a revolution, which is MCMC, as it's called, Markov Chain Monte Carlo. That there was some papers by Alan Gelfand, Adrian Smith, and a few other people that came up with a very, very, very simple way to compute the posterior distribution. In fact, it turns out it had been discovered during World War II when they were making the bomb, and somehow in the field of statistics we forgot it. I don't know exactly the historical reasons for that. But the method had actually been around for quite a long time, and so I guess you could say we rediscovered it. And this was a really, really exciting development because we were doing Bayesian estimation for models with 2 or 3 parameters. All of a sudden, we could do Bayesian inference for models with 20 parameters, or 50 parameters, or 100 parameters, or 1,000 parameters. And that changed everything because all of a sudden it was no longer just a philosophical argument. People were actually using it. People were using it for all kinds of problems. And all of a sudden, everyone was a Bayesian. Not everyone, but it was a pretty exciting time because when you couldn't compute something and all of a sudden you could compute it, you know, everybody just gets interested, and there was this flood of papers about how to do Bayesian inference for this problem, how to do Bayesian inference for that problem. And so it was getting used a lot. And it went from being kind of a philosophical corner of statistics to something that was being used routinely for people's data analysis. But here's the problem. The models started to get bigger and more complicated. And so typically today, when we deal with statistics problems, it's not uncommon for us to deal with very high dimensional problems. We might have thousands and thousands of SNPs, single nucleotide polymorphisms, in our genes and just proteins. We might have thousands, millions of things like this. So all of a sudden, the number of parameters we're dealing with is no longer 5 or 50 or 5, it could be thousands and millions. And it turns out that when we deal with large, complicated models, we're back in flatland. This is the case, precisely the case, where Bayes methods and frequentist methods give different answers. And so all of a sudden, we're back to the place where it matters, where actually when you're analyzing, say, bioinformatics data, it actually will, you can get very, very different answers whether you use Bayesian methods or frequentist methods. So here's an example. You want to predict a complex disease from, say, 50,000 genes. You have to estimate 50,000 parameters. And all of a sudden, these two different approaches, these two different philosophies for doing statistics will typically not yield the same answer. Then computer scientists got into the action. They rediscovered statistics and called it machine learning. Just kidding. Just kidding. And probably just, if there's any computer scientists in the audience, I apologize, that's just a joke. But it's true. Machine learning. What's true is that computer scientists did get involved in data analysis, which actually is great. I mean, I am firmly appointed in machine learning, and I love my machine learning colleagues. But the interesting thing about machine learning is people doing machine learning have a lot more, in Yiddish you'd say chutzpah, I don't know how to translate that, but a lot more nerve when it comes to jumping into problems. Statisticians are these kind of shy, retiring, conservative types of people, like, oh no, that looks too hard. Computer science will predict, things with millions of variables. Sure, we'll do that. And they jumped in, and there's actually quite a similar split happening in machine learning. That you'll see that there's a kind of Bayesian, a lot of papers or institutes with Bayesian flavors to them, and then there's the whole frequentist world. Similar kind of thing playing out there that played out in statistics, as well as in other fields. And of course, the computer scientists are really good at computing, so the problems that they could work on were staggering. So now we can compute both the frequentist and the Bayesian answers in very large complex models. And of course, this is now happening in biology and astronomy, high energy physics. You just name a science, and of course people now deal routinely in all sciences with very high dimensional models. And I mentioned, let me go back to astronomy that I talked about earlier, that we have this astrostat group here, modeled much like after the one here. And a lot of times our astronomer friends come and they say, we're having a problem with this analysis. Well, I'll tell you, this is a very specific example. This is a true story. So one of our colleagues says, I have this problem, can I talk about it in the group? We said, sure. So he presented it. He decided to do a Bayesian analysis. He went through the whole thing and he showed us everything. And I said, it looks correct. Everything looks correct to me. And why are you dissatisfied with this? And then he showed me, he simulated it. And he realized that the 95% posterior intervals he was computing were not containing the true value 95% of the time. And I said, but this is a Bayesian thing, it's not supposed to be a frequentist thing. They don't have anything to do with each other. And he went, it's like something he intellectually understood from a very smart guy, but when he was actually faced with it and realized that they could be different, it hadn't sunk into him before. And I think this is happening a lot now in lots of fields, especially when now we're dealing with these high-dimensional models. So the answers can be very different. And again, it's not that one is right or wrong, it's just they're answering two different questions. A little bit of theory I'd like to mention here, the kind of historical note. I just want to give a little historical note that's been overlooked. Let me just check my time. Okay. We shouldn't be surprised that the Bayesian methods and the frequentist methods can give different answers in high-dimensional or complex models. Dennis Cox, in 1993, published a paper, The Analysis of Statistics, which pointed this phenomenon out, although admittedly in a somewhat dense, hard-to-read paper, but the message was there. The late David Friedman wrote a paper about this in 1999, where he showed, again, that in high-dimensional models, you can have something which has a very high degree of belief, but if you ask how often would it travel true value, it could be zero, actually, or close to zero. Robbins and Ridoff wrote a paper in 97 about this. So there was actually, the writing is on the walls, and although I think a lot of people ignore this theory. But in high-dimensional models, the point is this, that it can be the case, it doesn't have to be the case, but it can be the case that you can find a set and say that my belief that the thing I'm trying to estimate is in this set, given the data, is very high, let's say 95%, and yet, in all of these examples in these papers, they show that the frequency with which the set of traps A could be close to 0. And again, it's just saying that frequencies and beliefs are two different things. That's all it's saying. And then I have to mention that David Friedman was one of my favorite statisticians, I have to say. He was a tough guy, but he did a lot of smart things, and he had this fantastic theorem all the way back in 1965 that I've seen very few people mention this. And he basically pointed out that the disagreement between these two approaches is typical rather than exceptional. And the way he cast this was very interesting. He said, imagine that nature, or let's say your friend, is going to generate random integers from some random number generator P0. So think of P0 as a random number generator. So you're going to get these numbers, x1, x2, x3, and you can get them forever. And they're going to come from this random number generator. And each of these numbers is just a number, an integer. 1, 2, 3, 4, 5, whatever. And what do we know? Well, I know that this random number generator, or this probability distribution as we call it, is just some random number generator. And so it's contained in what I wrote there as script F, the set of all distributions, the set of all random numbers. That's all I know about it. So what Friedman asks is, well, what if we take a Bayesian approach and follow the mechanics of Bayesian inference? I'm going to express my prior beliefs with a prior distribution, let's say pi, over the set of all random number generators. And then I see this data set, let's say the first 1,000 random numbers, and now I use Bayes' rule to compute this posterior belief. So I take my prior, I follow this prescription. I apply Bayes' rule, and I get my posterior. This is what I believe about the random number generator after seeing the data. And the question he asked was, as I get more and more data, do my beliefs, is the set of random number generators that have high belief in, are they getting closer and closer to the true random number generator that I'm generating? This is called consistency. So it would look pictorially like this. It's a little bit hard to draw the set of all random number generators, but let's just imagine every point on the x-axis somehow represents a random number generator. And you somehow put down your prior, which is how likely you think it is that I'm going to use this one, this one, this one, this one, this one. Then I give you this long stream of random numbers, and now you keep updating your beliefs using this Bayes theorem, and hopefully it would collapse around and crunch near the true random number generator. And if that happens, we say it's consistent. And if it doesn't happen, if this thing collapses at the wrong point, or just never collapses, we say it's inconsistent. So there's two things in this game. There's me or nature, whoever's picking the random number generator, somebody's picking this P0. And then there's the data analyst who starts the whole process off with this prior, P, which is these beliefs about the random number generator. There's just these two things, pi and P0. And now I can ask, given pi and P0, do we get this nice phenomenon like in this picture, that our beliefs are piling up near the truth? And what Friedman showed was that it essentially never happens, that the set of pairs, the set of random number generators and priors, such that you get consistency, forms what's called a meager set. It's a topological term. It basically means very close to an empty set, you might say. It's like dust, you can barely see it. So in other words, it's very, very unlikely, in some sense, that you would ever pick that if I pick a random number generator and you pick a prior, that you're going to see that you'll ever get consistency, that your beliefs will ever converge to the truth. And in fact, he even said if you had two different people with two different prior distributions, you could ask, will they converge? Will they at least come to the same posterior? The answer is they don't. And the way he put it in his paper, which I really love, is he said most pairs of priors leads to inferences that disagree. It is easy to prove, in other words, that for essentially any pair of Bayesians, each thinks the other is crazy. That was a great thing in a very technical paper to be able to sneak a sentence in. Now there is a very reasonable Bayesian response, which is that's imagining that I'm picking a random number generator somehow, and you're just somehow picking some prior distribution to represent beliefs. But there's a good response, which is that it turns out that if you're going to do a Bayesian analysis of this problem, you can choose the prior carefully. don't just choose any prior, you can choose a prior in such a way to force it to be consistent. You can say, of all the billions and infinitely many priors I could pick, I'm going to construct one that guarantees that Larry gets that nice picture, that my beliefs converge around the truth. And you can construct a prior, to which I say, congratulations, you're a frequentist. Because you've given up on Bayesian inference. You're no longer using the prior to describe your beliefs. You're just trying to recover good frequency behavior. And this is sort of the Nate Silver world, where you're using Bayes' rule, but you're not really doing what I would call Bayesian inference. You're no longer trying to represent your beliefs. You're just trying to get good frequency. Okay. So the bigger picture here, to bring it well with the time. Great. Yeah, I'll even finish it later. Let me just say what the big picture is, which is really what I wanted to say is, statistics can seem very, very dry to people who aren't in statistics. I've even had colleagues go, statistics, that's a field? Like, there's actually departments, there's people doing research on that? I mean, and I'm talking about colleagues at, universities. Stats somehow has this kind of bad reputation that it either doesn't exist, or we just do baseball scores, or we work on the census, and it's kind of a boring field, and the only thing we're only one step above accountants or something like this. Jay Leno, I remember the American Statistical Association had its conference in LA, and Jay Leno thought this was the funniest thing. So every night that week, he had some joke. He said, "Oh, wouldn't you like to be the pocket protector salesman at that conference or something?" He had some sort of joke about statisticians every night. But statistics really is an interesting field. We're not crazy. We actually work in this area because it's interesting. So what I really tried to do was I wanted to pick something that showed you that, philosophically there are interesting debates and interesting subtleties that we do have to deal with in statistics, and they actually affect the answers. I mean, really, what I present when I analyze data for someone, maybe I'll use a Bayesian method, maybe I'll use a frequency method, but the important thing is that I explain it very carefully to the person and tell them what I'm doing. But there really is some interesting subtle points in statistics. So I hope I managed to convince you that there are interesting subtle ideas in statistics. There really are deep philosophical issues, and they do affect, again, what happens when you take a medication. In fact, there was some debate for a while that should the Food and Drug Administration be using Bayesian or frequentist methods for clinical trials when they approve drugs. And my understanding is currently the standard actually is to use frequentist methods, although there is some movement to try to introduce Bayesian methods, and there are times when I think that would be appropriate. Again, the key is to make sure that the people at the FDA understand the difference and when they should use which one. But the point is that this philosophical debate really affects everybody. And especially now, because this is the era of big data. Data are everywhere, or data science if you want to call it. Data are in every single field now. There's very, very little in society that isn't touched by data. And when you have data, you have to analyze it. And when you're analyzing it, whether you realize it or not, you're either using a frequentist approach or a Bayesian approach. There are a few other flavors of statistical inference, by the way, but they're smaller players compared to these two big guys, which is why I've concentrated on that. So this affects all of us, and it's going on all the time. And statisticians obviously have to do a better job, I think, of getting our ideas across and educating everybody about it. People are using statistics, pharmaceutical companies. Google does the largest randomized clinical trials in the world right now. Every time you do a Google search or randomize into an experiment, they're using statistical inference methods, Facebook, and so on. They're used all over the place. And so the point is that this is not just some sort of idle philosophical argument, but it actually affects, I think, a lot of things that we use every day. The question in each case that I think we have to ask is, go ahead and compute things with data, but always ask, what are we computing? And we need to explain to people that the numbers have a meaning, and we have to be clear about what those numbers are. So to say who's right, both approaches are correct. They're just answering different questions. Both frequencies and beliefs are based on sound mathematical theory. They're both mathematically valid, but beliefs are beliefs. They're not right or wrong, this is somebody's beliefs. Frequencies are frequencies. How often do you get something right? They are right or wrong, by the way. They're testable, because if I say I have a 95% confidence interval, you could simulate it and see, does it actually work 95% of the time. But the point is that they're just two different things. And of course, users and newspapers need to understand the difference. So let me conclude by going back to the original question at the beginning. So the thing I pulled off the web, it was actually from a study that I found on the web, was it said literally, we are 95% certain that the effectiveness of, that should be of, the flu vaccine is between 0.255 and 55, and they were very clear in the paper. They were computing a confidence interval. They were using frequentist methods. In other words, they were using software for computing that interval, 0.25 to 0.55. They're not making any statements about what they believe about the flu vaccine. They're just saying that that software traps the true value 95% of the time. In this instance, it either did trap it or it didn't. There's no beliefs. It either worked or it didn't work. But we know that the method does work 95% of the time. The IPCC, we are 95% confidence humans are the main cause. That turns out to be a belief. And there's a very interesting long story there that I read about the debate that took place at the IPCC between, I've forgotten the gentleman's name, who led this idea that the IPCC should state beliefs and publish them, and there were a bunch of econometricians who were opposed to it because they felt it was subjective and didn't have the meat that frequentist methods had. It's an interesting story that obviously I won't get into here, but what I do want to get across is these are just two examples that are obviously both very important, and they're both right. They just mean different things. One is a frequency, one is a belief. So the bottom line to conclude, beliefs, Bayesians, frequentist methods are both useful. We just got to make clear to everybody that they're different. And with that, I thank you for your attention.
So we're going to open this up for questions, and we have two choices here. Either I could run around like a crazy person and try to hand the microphone to everybody who asks a question, or my preference would be that, Larry, can you just repeat the questions for the benefit of people who are streaming this?
Oh, sure.
Questions?
Yeah, so I'm kind of surprised by your non-regenerative because I thought back in the day, sometime maybe around the 90s, was say, well, we have this, we can't capture all of our beliefs, or rather, there's a large number of different factors to capture what we actually believe. And so what we ought to do is pick the ones that give us consistent answers so that we can actually do both.
So I guess Naomi's question is that in the 90s, didn't people conclude we really couldn't capture beliefs, so we should choose priors that have good frequency properties?
Well, but they'll capture what we do know.
But do capture, but do have, so try to get the best of both worlds. I certainly, that would be an in-between position, which is try to use priors that capture parts, things, aspects of our beliefs that we're confident about, otherwise still have good frequency properties. I think that's possibly true. I think it depends. I won't name names, but I think there's lots of people who would disagree with that statement, who view themselves more in the Bayesian camp, that what we should really be doing is quantifying our beliefs. But then I think there's some pragmatists like maybe me and you who would say that's a perfectly reasonable thing to do. Although I would say it's far from obvious still to me how to do it and build complicated models. But yeah, if we can get the best of both worlds, that would be wonderful.
Okay, I have to say that all the questions are coming from this side of the room. It's easier for me to do this. So.
Well, I forget which philosophical view, basics of philosophy of sciences comes from, but for something to be sort of a scientific principle, it needs to be testable. That's something that one talks about. So when you lay things out as you did at the end, when you say beliefs are not testable, it just sounds like that's not science.
So that's an interesting point. I guess that's the Popper philosophy, right? That science has to be testable. And so from that point of view, you'd say frequency methods are testable, Bayesian methods, beliefs are your beliefs. There's nothing testable about them. But I think, so I'm not a philosopher of science, so I guess I can't really answer your question and say that definitely would, tilts things one way or another. I would imagine that there are philosophers of science who argue that the Popper idea maybe is an oversimplified version of the philosophy of science, and that there probably are cases where things are not exactly testable, but they would still consider them scientific.
I guess the climate example.
Climate, and I think a lot of things about like particle physics and so on. But yeah, if we take the Popperian point of view, I guess you're right. That makes frequentist stuff from that point of view more scientific. But I don't consider myself a philosopher of science, so I think that's a good question to ask somebody in the philosophy department. But I don't want to stay up here. I'm weaseling out of this because I don't want to claim to have some expertise in the philosophy of science that I don't have.
Dennis?
Yeah, just curious. Can you tell people how to improve their belief, or believe just believe? It doesn't matter whether good belief or bad belief. Is there any way people can learn how to make a better belief?
That's an interesting question. Is it possible to learn how to improve your beliefs? And since I offloaded the last question, I'm going to do that. I'm going to do that to the cognitive psychologists, because we know, of course, there was this series of experiments by Tversky and thank you, that showed that people are pretty bad at making up quantifying beliefs, but I presume that there maybe are methods that can help train people to quantify their beliefs better. I'm skeptical, however, so I think for certain everyday things we can do that. I'm skeptical, though, that in a statistical model, with 1,000 parameters, that anybody could ever quantify their beliefs well about 1,000-dimensional space. So they might be improvable for some aspects of it. I guess if I combine your question with Naomi's question, if we could create priors where you only have to express beliefs about certain parts of the problem, and then if we can improve our ways for quantifying our beliefs about those aspects, then perhaps that would be a useful move. The MC, he'll decide.
I'm what of a layman had in the area. I want you to please explain to me once more the difference between the Bayes rule and the Bayesian inference.
The difference between Bayes' rule and Bayesian inference. So Bayes' rule is just a theorem of probability that's completely uncontroversial. It just says that if I have a distribution, probability distribution, and I observe new data, here's a rule to update it. Bayesian inference is more about the interpretation of the goals of statistical inference and the interpretation of probability. In the Bayesian inference, as I understand it, is the goal of statistical inference is to quantify people's beliefs about things and then to update those beliefs, to quantify them and update them. And it so happens that in doing so, you end up using Bayes' rule. But you can use Bayes' rule in certain frequentist methods as well. So it is a little bit confusing, but one's just a mathematical rule, and one's kind of a philosophy about how to do statistics. I hope that helps.
So I'm a cognitive psychologist.
He's going to tell you how to do it.
So humans actually do both the beliefs and frequentist methods, and we see that from very early on. The babies, the infants start to do both approaches. So from that point of view, I think it's very hard to get to a second goal to teach the public and the rest that there are different things, because we implicitly actually use these beliefs and frequencies. I think from a cognitive psychology perspective, is how we can teach them apart. At one stage, does the child rely more on frequencies approach versus on beliefs? I think from some of our own research, we actually can see at some point they actually switch. The baby who is exposed to normally would, for example, we have a model that shows if the child is learning one language, they have they rely on one belief. But when they're exposed to multiple languages, they have to change that belief and rely on a different belief. And the Bayesian inference models are very helpful in modeling these kinds of learnings.
But what you're saying is it's going to be hard to actually explain to people what the difference is.
Because we implicitly use
Because we
both.
use both.
And we mix them up all the time.
Yeah, but the statisticians mix them up all the time.
So I'm curious, when you use this, the binomial machinery, what comes out in the end? Is that a frequency, a belief, or is it like a belief about a frequency?
I would say, well, that's a really good question. I mean, to me, what you're getting out are frequencies, because it's basically tuning the machine to give you good frequencies. And so I view it as, like in Nate Silver's book, that what he's getting out are frequencies. And so, to me, the beliefs have almost disappeared from that guy.
Don?
Larry, I find it very easy to test people's beliefs. When I teach probability, in fact, back in January, when students were all claiming that the New England Patriots were going to win the Super Bowl, I said, well, why don't you offer me 19 to 1 odds? And they all said, no, we won't do it. I said, well, okay, offer me 10 to 1 odds. And I took out a 20 and I put it down and I said, if you win, keep it. If you lose, you owe me a couple of $100. And by just changing the odds, they suddenly start realizing that they don't believe what they
Actually, Don raises a really important point, because if you read books on Bayesian inference, that is how they'll talk about what's called the listening people's prior beliefs, which is you just ask them to bet. That's the father of Bayesian inference, in some senses, was this Italian statistician, Bruno De Fedeli, and that's how he phrased the whole book, was what odds were people willing to bet at. That's great for the Super Bowl. Now get your students to do that for a high-dimensional, non-parametric regression in Sokolov space with uncountably many parameters.
I want to test my naive point of view as a physicist about this topic. Imagine I have some experiment that is producing data, and I have two models. Each model has a set of parameters that describe them. Am I right to think that if I want to guess the parameters given in model, I have to use a frequency analysis? But if I want to decide between the models, I have to use a bias analysis in such a way that a belief is essentially how good is a model to describe nature. Is that a good definition?
So the question is, if I have two models, and they each have sets of parameters, the suggestion was maybe we're using frequentist methods to estimate the parameters and Bayesian methods to compare the models. Actually, both problems, which I would call the first one estimation, and the second one model selection, both can be done either from a Bayesian point of view or from a frequentist point of view. So you could do Bayes, frequentist, Bayes.
Yeah, so what resonates with me is this idea that these two ideologies are fundamentally measuring two different quantities that are incompatible. So an idea is that the cornerstone of hypothesis testing, for example, which is in a frequentist framework, it formulates this hypothesis, which is sort of a belief. But if you want to use a frequentist framework for estimating this belief, how does that exactly sort of go hand in hand in a frequentist setting?
Well, again, so I think the question was like when you're doing hypothesis testing, how to interpret
the presence of a belief and a frequency measure, which are fundamentally two very different.
That's right. So I think it's another example, like the last thing where you can do hypothesis testing from a Bayesian point of view. You can do hypothesis testing from a frequency point of view. And I think you're hinting at that there's probably a lot of misinterpretations of it and a lot of misuses of it in hypothesis testing in general. But again, I think from my point of view, it can be done from either point of view. And the hard part maybe is just being, especially admittedly, trying to teach this to students, I think it's often difficult to communicate. Yes, those things they're computing on the frequencies of which are not beliefs, even though they might want to interpret it that way, and vice versa. So that's a case where it's especially difficult, I think, to communicate the difference between beliefs and frequencies.
So, would you be comfortable with the FDA? I
Bayesian perspective, not just but they actually said we believe 95% that this drug won't kill you. That's something you would be comfortable with?
Well, that's, oh, he said, would I be comfortable with the FDA?
Yeah, it's your belief.
Using Bayesian methods for drug approval. Next question. I don't know.
I think the methods are quite powerful, but I think the moment you start getting into this sort of belief philosophical debate, I feel like you're going to lose against things like, science, testable beliefs, FDA, these sorts of things, because it's very hard to convince somebody of that, right?
Yeah, I mean, the stock answer would be if I had a very expensive treatment and patients were coming in very slowly and we have a lot of prior information about that treatment, then we might want to use prior and then update it as we go along, and we might get a much more efficient clinical trial. On the other hand, the problem we face is exactly what you just said, is people would say, well, maybe I'm not comfortable with this. I suspect, I'd be curious to know the public's reaction to the IPCC statement if they understood that it was of this type of statement. I don't want to take a position on it. I guess I'd want to know who was the statisticians were running.
Over here.
Okay, so as someone without very comp sci experience, can you explain the flatland example? Because in my mind, I just see it as there's a 25% distribution for all sides. So why wouldn't it be that 75% either northwest or east?
So why does it come out in the flatline example that even though that 75% belief set seems perfectly reasonable, that it doesn't win 75% of the time? It's actually a high-dimensional example because the set of all paths in the space is very, very large. And so this is an example where there's theorems that will tell you when the Bayes and the frequentist thing tend to agree, and they tend to be in these smooth, low-dimensional problems. So I'm probably not giving you the least bit of intuition at this point, I realize, but why it comes out that way. I actually don't know how to explain why it gives that answer without just doing the calculation. It's just one of those things where it's very, like I said, it's so surprising that when I put this on my blog, I literally had famous statisticians writing me saying, you're wrong. And I would tell them, read Stone's paper in 1973 or whatever it was, and you'll see that the calculation is correct. And then they go, oh, okay. But it's not the least bit intuitive, I guess is the answer, because otherwise I wouldn't have had all that hate mail. I'm sorry, that wasn't probably a satisfying answer, but it's...
So do you have like a computational proof on your blog?
If you look at my blog, if it's still up there, I have the reference, and that's the best place to look at the original references. Well, it's proved as theorems and so on.
Over here on the other side.
Trying to put together a lot of the questions that have been done. I think the key of where of the methods work best is when the data is available or not. For example, if the question about the FDA, if there is no data about a new disease, but there are experts that know similar diseases, the frequencies will not do much because there's no data to test the frequency. The patient will do better. But then, from that, you can run experiments to get data to frequencies type of analysis. So I think the key is the availability of data to do each one.
Yeah.
Is that a fair assessment?
I think that's a good point. In fact, here's another example, an extreme example of that, which is when it comes to designing experiments, you might say everybody's amazing because you don't have any data yet. So the best you can do is you can say, well, if I think these are likely values of the things I'm trying to estimate, then this is the optimal design. And it's pretty hard in general to do an optimal experimental design without somehow, at least implicitly, expressing some sort of belief because you have no data yet. And so that's a case where I think you pretty much have to use data.
And Naomi?
So I don't understand how that point of view can be true if Bayesian methods aren't consistent.
Well, they're not consistent in some cases. I didn't say they were always inconsistent. it's basically in high-dimensional or infinite-dimensional models that are not consistent in general. But if we're just imagining a clinical trial with a single parameter, a treatment effect, then of course it will be consistent.
I'm going to arbitrarily declare that we'll try to wrap this up by 20 after session.
Just a quick comment back to the question that we had about the floodline example. So maybe it's worth pointing out that Frank's 75% is based on the algorithm she chose. If she would have chosen a different algorithm, I think Larry's point was not that Frank is going to win over all the time. If she would have chosen a different algorithm, she also could have gotten 25% coverage or 25% confidence interval depending. So there's also that issue that you have to keep in mind.
Right, she had to choose the right algorithm to
Right.
make sure she went 75%.
Other questions? Okay, one last question then.
It's more of a, I'm interested in how your thoughts on this have changed since your grad school days. Because you said this debate made, and then you stopped talking about it, and now you're talking about it again. And I'm wondering if there's any difference, or if people are making different arguments, or if it's just the same people making the same arguments.
Well, they're all older now. But I think that there has been a waxing and a waning of interest. I think there was a lot of interest, oddly enough, when people couldn't compute things because we didn't really know how things were going to come out in some sense. And so in those days there was a lot, it was discussed all the time. I think when the MCMC stuff came out, everybody said, we can compute things now, let's just work on applied statistics and forget about philosophy. And so I think it was just the excitement of being able to compute answers. We all put it aside, maybe not all of us, but there was much less interest in it. And it really sort of died out. Now it's not so much that it's people are arguing about it again, so much as that I'm saying I think it's relevant again because I think people are computing things and not always knowing what they're computing. This is what I see all the time in the various people that I work with. But I'm not sure that the interest was probably higher years ago, to be honest.
Well, with that, let's thank Larry again for an great talk.